Okay, one last batch of stuff to say about the Taylor and Maclaurin series. So at the end last time, we had come up with these three important Taylor series. E to the x, why did I put z there? I don't know why. E to the x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, etc. I'll go up to the fifth one, or the x to the 5 one. All right, that's e to the x. It's a little strange. I wrote 1 over 2 factorial. 2 factorial, of course, means 2 times 1, which equals 2. So if you like, you could just write 1 over 2 here. Although I put the factorial just so that everybody can see clearly the pattern here. This says 5 factorial there. All right, you always get 1 over n factorial x to the n. That's the Taylor series for e to the x. These factorials are part of every Taylor series, and it so happens that in e to the x, you just don't get anything else. We also talked about sine and cosine. So the sine actually only has every other term, and the sine only has the odd ones, and the sines alternate. And I'm going to try and line them up in a suggestive way here. The sine only has the odd powers, and the plus minuses alternate in the sine. And the same is for cosine, but the cosine only has the even powers, including the 0 power, which is the first term. So the cosine is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4. The next one would be minus the x to the 6th term, etc. All right. These are the Taylor, actually these are the Maclaurin series for e to the x, sine x, and cosine x. Maclaurin just means it's the Taylor series centered about 0. All right. These ones I said you should memorize last time, although to be honest, this is probably not necessarily. I said that because, well, it's because of the part that we skipped. You know, we're skipping number 24 on the big list. If we had done that one, you definitely would need to have these memorized in order to do that stuff. But we're not doing that, so to be honest, you probably won't have to memorize them. But these are super important and deep facts in calculus. I would say, like, as a responsible citizen and calculus enthusiast, you should know these. But it won't necessarily help you out on the test if you have these memorized or not. All right, what I wanted to talk about, one thing today, is the relationship between these three. And this is something that I mentioned at the very end last time. It seems like, so sine they're basically the same stuff that you're writing here and here. It's just that sine has all the odd numbered ones, cosine has all the even numbered ones. But if you were to add these up, sine of x plus cosine of x, they would kind of like fill in the blanks and you'd get that, right? Now, this is not exactly true, what I just said. You wouldn't get this because of these minus signs here. It's different, right? If you added sine plus cosine, these would actually add up together, but these are negative, but in e to the x, they're positive, all right? So I would say, as far as I suggested at the end last time, maybe there is some like deep and undiscovered relationship between sine, cosine, and e to the x. At a very simple level, there isn't because of those signs. They are different, and that really does make a difference. But somebody figured out a cute trick, and this was worked out by Euler. Euler is responsible for a whole lot of things. Living in the 1700s, he figured out tons of stuff that is super important. Euler realized this pattern of the signs, you know, here the signs are, if you were to add these together, the signs are not quite alternating. It's like positive, positive, and then a negative, negative, and then a positive, and then a positive, and then a negative, and a negative. This same kind of pattern, Euler realized we can make this pattern of the signs using the imaginary number I. This is the definition of I is the square root of -1. Now, it's called an imaginary number because it's not a real number. Although the name imaginary number is kind of overly suggestive. You might be tempted to think that these things don't really exist, and that's not true. They are. It is a thing that exists. It's kind of like infinity. Infinity is a thing that you can talk about. It's not a real number, but that doesn't mean like there's no such thing as infinity. That just means it doesn't qualify as a real number, but it's still a thing that mathematicians like to talk about. I is the same way. It's called an imaginary number, but that doesn't mean that it's not a real thing. It is a thing that you can talk about if you want to. And I actually comes up in real life all the time. I is like if you want to work out the mathematics of electromagnetism, you must use I. So, it does exist in reality. It's just not a real number. But anyway, check it out. If you start with I, all right, I'm just going to write of course, I equals I. I'm going to write out the powers of I squared, or let me start actually with I to the 0 power is 1. That's because anything to the 0 power is 1. I to the 1 is I. What is I squared? Well, if I is the square root of 1, I is the square root of -1, I could square both sides here, and it says I squared equals -1. So this is -1. What about I cubed? This is a little confusing, but you can think of I cubed as the same as I squared times another I. Like each one of these, you would multiply the previous one by I to get the next one. And if I squared is -1, I multiply that by I get -1 times I, which is -I. All right? And then I to the 4, by the same reason, it would be this one, -I times another I. That would be -I squared. But I squared is -1. Negative times this is -I squared. But I squared is -1. So that's -1, which is 1. I to the 4 is 1. Positive 1. It becomes, so this I, when you do these powers of it, it sort of turns into a real number. It's a real number. Even I squared is a real number. And then you get this other imaginary, but then it's the real number 1. And then what is I to the 5? Well, I to the 5 would be the previous one again times I. This is I again. And actually you get this kind of, what you have here is this sort of repeated pattern in blocks of 4, right? You go 1, I, -1, -I, and then 1, I, -1, -I. This will repeat forever. And Euler must have realized this is exactly the same repeated pattern that we saw last time when you try to do the Taylor series for sine and cosine. You get this kind of repetition in blocks of 4, and it's exactly this same pattern, not with i's, but with sines and cosines. You get sine and then cosine and then negative sine and then negative cosine, and then it repeats again. All right. So check it out. Euler had this big idea, realized that there was some kind of connection between this repeating pattern here. I imagine he had to think about it for a while, but eventually he came up with the way to actually make this connection work out. If you plug in, start with this formula for e to the x. I'm just going to copy it so I don't have to keep scrolling. And I'm going to plug in, so start there, which Euler already knew this formula, and I'm going to plug in ix for x. So not just x, but plug in I times x. It will say e to the ix is 1 plus ix. Every x I change to a ix. So this is going to say 1 over 2 factorial. So this is x squared. It'll become I squared x squared. I'm replacing every x by a ix. 1 over 3 factorial, I cube x cube. 1 over 4 factorial, I to the 4 x to the 4. 1 over 5 factorial, I to the 5 x to the 5, etc. Right? I just replaced all the x's with ix's. But now, according to those patterns up there, these blocks of powers of I, you can simplify the powers of I here. This one is just I, you have to leave it like that. 1 over 2 factorial. Okay, now this one, I squared, is the same as -1. Would you mind if I just make this a minus sign here? I squared is -1, so this one becomes that, right? And then I cubed. I cubed is -I, so I'm going to write the next one as minus I times the other stuff, like so, right? plus I to the 4. I to the 4 is positive 1. And so that is just, we can just sort of leave it out. All right. And then I have I to the 5, which is equal to I. So this one I could just put I there. All right, etc. and so on. I hope you're still following along. We're pretty much done with where this is going. Check it out. I would now invite you to observe. If you look at the even ones, the even powers, I see this, 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 etc. Those are exactly the terms of the cosine series with the proper plus minuses, right? It's a positive, if you scroll up to the top. Cosine has a positive 1, then a negative 1/2, then a positive 1/4. 1 over 4 factorial, and so on. So those are, the red stuff is cosine. And the other stuff, these guys, the green guys, those are sine of x, but everything has an I in front of it, all right? Sine of x has x and then negative 1/3 x cubed and then positive 1/5 x to the 5. So the green stuff which you see there is sine of x times I, right? Everything has an I in front of it with the proper plus minus signs, all right? So the final thing then, so all of this put all together, it means that if you do e to the ix, which is what we started with on the left side here, what it is just these two things added together. It's cosine of x, which is the red stuff, plus this is usually written as I sine of x, all right? And this is referred to as Euler's identity or Euler's formula or something like that. This is the relationship between the function e to the x and the sine and cosine functions, all right? It is something that, according to like the historical development of mathematics, no one expected this to be true, and it's a strange thing to think about. It sort of makes, when I think of this formula, it makes me think about things like, where does mathematics come from and what is the purpose of mathematics? The typical answer to that question, where does math come from, is people invented math, and that's why it exists. And what is its purpose? The purpose of math, people invented it in order to like solve problems in their real lives, or to eventually like to do science. That's why math exists, and that's why people made it. And that's true, what I just said. That is why math exists. But if that's all mathematics is only just a tool to be used to do things, then things like this ought not to be true. This is a thing which turns out to be a true fact in mathematics, but it has nothing to do with the reasons why cosine and sine were invented. Like sine and cosine are invented to do geometry, trigonometry, and e to the x was invented to do like exponential growth calculations in, compounded interest, that kind of thing. These, on their surface, and according to the people who created them, should have nothing to do with each other. But in fact, they are related in this very simple and deep way. This is a profound mystery. If mathematics is only a tool that is invented by human beings, then why are there like surprising things in mathematics? There's no good reason for that. But it is the way that, that this is just a fact about what math is. Strange thing to ponder. I don't know if you ever think about this kind of thing. Tools which are invented by people ought not to interact in this unexpected way. It's kind of like, if somebody invented a helicopter and then somebody else invented an ice cream cone, and then somebody discovered, oh, you can actually like make a nuclear particle accelerator if you just like stick together a helicopter and an ice cream cone. The answer is like, no, those are two different things. They have nothing to do with each other, and you're not going to get some kind of magical other thing by combining them. But actually in math, that really does happen. This has led some people to suspect that the impression that you get is not that math is being created by human beings, but somehow math is already existing as part of the universe, and we're just discovering it. And to me, as a mathematician, like that's part of what is inspiring about math to me is that kind of both of these things are true at the same time. One very cool thing about this, check it out. You can actually plug in a particular value here, and you get really nice results if you plug in x equals pi. What that would say on the left side would be e to the I times pi, and on the right side you get cosine pi plus I times sine of pi. And we know, just because we know sines and cosine, the cosine of pi is -1 and the sine of pi is 0. So this actually says e to the I pi equals -1 plus I times 0, right? I times 0 is 0, of course. So this says e to the I pi. I wrote it pi I. Either way, I guess. E to the I times pi equals -1. Sometimes people like to write this formula like this, e to the I. If I just add it over to the other side, like that. This also, in a box, this also is sometimes called Euler's identity or Euler's formula. And this is like typically, if you ask, say, like a random mathematician off the top of their head, like what is the most beautiful formula in all of mathematics? This is typically what people will say. Euler's formula about e and I and pi and 1 and 0. Why is this regarded as beautiful by mathematicians? It's because this is a single formula which combines, I would say, sort of like the 5 most important numbers ever. If you ask me, like, what are the 5 most important numbers? Of course, you got to have 1 and 0 as like the GOAT numbers, right? Also, if you want to do geometry, pi is the important number from geometry. If you want to do calculus, e is the important number. And if you want to do algebra, then I is the most important, like, non-real number that you use in algebra. And what this is a combination of all, this is like the greatest, the 5 greatest numbers ever, and they all were invented to serve different purposes in different historical periods, but somehow they all actually are related in this way, which nobody, like I said, nobody ever would have expected that these numbers would be related in any way at all, but they turn out to be related in this way. I believe this formula is written on Euler's tombstone, and this is like typical go-to math tattoo idea. You know, some people have math tattoos, and this is kind of like the junior in college math tattoo, like people who don't actually know a whole lot of super specialized. Like if you ask me what's the most beautiful thing in math, I'm more like my true answer is more likely something in my own particular research area. But as a kind of like mainstream, this is like saying your favorite band is the Beatles. It's like, okay, fine, like, and actually my favorite band is the Beatles, but like you're saying something that like everybody recognizes. The Beatles are pretty awesome, but it's like most people want to be a little edgier than that or something, a little quirky. This is not quirky at all, but it's definitely something that everybody thinks is great. All right, any thoughts about that? This is Euler's formula. It is an amazing true fact which has not a lot of good sort of reasons for being true, other than, you know, mathematically it is true. You can prove it. All right. I have one more thing to discuss, and then that'll do it for us. So we talked last time about finding the Taylor series of various functions, and we did these examples. I just want to do one more example, and then I have one for you guys to try out, and then that'll do it for us. So the typical homework problem, or the problem you should expect to see on our final exam about this, will say something like, here's a function, you find the Taylor series centered at whatever. Now, we haven't actually done any other examples using a different center point other than 0, so this is something to talk about. Let's try. I got one here. Find the Taylor series for sine of x centered at x equals pi over 2. All right. So sine of x is my function. F of x equals sine of x. And I want the Taylor series centered at pi over 2. And I will just refresh your memory. What that means, centered at pi over 2, it means we'll have terms like, something or other plus something times x minus pi over 2 plus something x minus pi over 2 squared, etc. Like the ones we were doing before, the ones that I wrote at the very top in a box, were always centered at 0. That means it's just x every time. But you can also do centered at some other number, which means you're going to write the terms of your series, and each one involves powers of, in this case, x minus pi over 2. And what are the coefficients? You have to remember the coefficients are an is 1 over n factorial f the nth derivative at, well, in this case, pi over 2, right? If you're doing centered at 0, you would do f the nth derivative at 0. But if you're doing centered at some other point, you do the nth derivative and plug in pi over 2. All right? So this is what we got to do. Really, the whole deal consists of finding these coefficients. All right? So I said find the Taylor series centered at pi over 2. Sorry, I meant to say something a little bit more specific. Let's just say write the first 4 non-zero terms. All right. And I'll say this on the test or whatever, just how many terms of the series that I want you to write out. Okay, let's try it. So really, the whole deal is this right here. These are the coefficients that we have to work out, and I think it's best to just start by these. The hard part of these coefficients is doing this derivative, right? The nth derivative. So we should write down, work out ahead of time, what are the various derivatives. Now this function is sine of x, which is not so hard to deal with. I will write the derivatives here are cosine x, and then the second derivative minus sine x, and then the third derivative minus cosine x. This is the same thing that we did last time, the same kind of pattern. And then after that, for the fourth derivative and further, it's going to repeat again, right? So it goes sine and then cosine and then minus sine and then minus cosine, and then the same pattern will occur again. Sine and then cosine and then negative sine and then negative cosine, and so on. All right, so those are the functions. And now what we are interested in over here is the nth derivative plugged in pi over 2. So in each of these, I'm going to plug in pi over 2 and see what we get. F of pi over 2. So here I hope everybody remembers what, you have to know what sine and cosine of pi over 2 are. Sine of pi over 2, the way that I remember these is just the graph. This is the graph of sine, and this is the graph of cosine. And pi over 2 is right here, all right? So sine of pi over 2 is 1. Cosine of pi over 2 is 0. So sine of pi over 2 is 1. All right, f prime pi over 2, this is cosine pi over 2, which is 0. The second derivative, you just got to work all these out. Negative sine pi over 2 is negative 1. The third derivative is negative cosine, which is going to be 0 again. Negative cosine pi over 2, which is 0 again. And then the fourth, I suppose you can do as many as these as you like until you see what the pattern is. After that, it's going to repeat in this kind of block of 4 terms, right? All right, and having worked out all of this, I think we're ready to write out our answer. So our answer will look like this. It's going to be a bunch of things added together with these coefficients, and also in our answer we have to include this 1 over n factorial, which we didn't include as part of this business here. So the series is, sine of x equals, okay, what's the very first term is just 1. It comes from this constant here, 1. So 1. Then plus the first sort of x to the power 1 term actually has a coefficient of 0, so you don't really need to write this. Maybe I'll just write it so that everything is clear. 1 over 1 factorial 0 times x minus pi over 2 to the power 1. Remember, each of our terms will be powers of x minus pi over 2. The next term is 1 over 2 factorial times the constant that we calculated up here for the second derivative term, which is this one, -1. And then times x minus pi over 2 squared. And so on, right? Now, I said specifically in the question, write the first 4 non-zero terms. So we do have a little bit of ways to go because this one is 0. So far I have 2 non-zero terms. So the next one would be 1 over 3 factorial times the third constant is also a 0, x minus pi over 2 cubed, all right? That one was also a 0. The next one is going to be 1 over 4 factorial times the constant, which I calculated up there, is a 1, and then times x minus pi over 2 to the 4. In terms of non-zero terms, I have this. This is not 0. I'm going to need one more non-zero term to have satisfied the question. Although the next one, the fifth power term, is also 0 here, just because of the pattern of these constants that we computed up here, right? The next one's going to be a 0, so the fifth power one will be 1 over 5 factorial times 0 times x minus pi over 2 to the 5. The sixth power one is not 0, and this will be the last one that we need to include. 1 over 6 factorial. According to the pattern up there, it should be a -1 this time. And then x minus pi over 2 to the 6. I'll just say plus ... So just to simplify things, the non-zero terms there are the 1 from the beginning. Then I have, instead of plus, I'm going to write it as minus because there was a -1 in there. Minus 1 over 2 factorial, x minus pi over 2 squared. The next one is the fourth degree term, plus 1 over 4 factorial, x minus pi over 2 to the 4. And the next one, or the last one that I'm going to write, is the sixth degree term, like that. This is what I want to see. I wrote the first 4 non-zero terms. All right, really it's just a matter of calculating these derivatives, these constants, and then you have to kind of appropriately plug them in, which looks kind of crazy here, although it's not all that complicated. All right, any thoughts about that one? I got one to try. I would like to write the Taylor series for f of x equals e to the 2x, centered at x equals 1. And I want you specifically to write the first 4 non-zero terms, and also write it as a summation. The previous one was kind of a pain to write this as a sum because it only has these even powers, which is a little bit of a little complicated. This one will be, I think, you'll be able to see the pattern easier in this example and write it as a summation at the end. See how you like it. Yes. Do your derivatives. Looks good. What are you gonna do next? You need to do plug the value in, and the previous one was like in garbage. This time unplug.
Sorry, what is accent?
1.
Thank you.
Yeah, so I got to scroll down. Maybe it never was gonna. Mm-hmm. You gotta do a good jingle.
Yeah.
Here we go. It says 1.
Thank you.
Scroll it. Alright. Yeah, great. You should start with just ETFs. That's it. It's, you do the chain rule, which means that it towards the end. But that should be for this one. This one is just.
That's it.
Yeah, perfect.
Is this right?
These should be just 2.
Okay.
Because you're doing the derivative multiply times.
Gotcha.
It's the chain rule. Great. Yep. Right. And you can see the pattern. You need to do this step before you start doing this.
Okay.
So you, this involves taking each of those and plugging them in.
Oh, gotcha.
Which here is fine.
Okay, thank you.
This is the 0 term. So it should be. Each term also has a power of x in it. Oh, this is. Yeah, this is a little weird, but yes.
Because you can listen to
You can say it again.
this one. So it's starts to repeat here.
Yeah, so I would say, I mean, there is a pattern, it's just you get equal to every time.
Oh.
And it's not repeating, but it's still identifiable.
Yeah.
What are you gonna keep there?
1.
Yeah.
Okay.
And you need these factorials always have to be.
Gotcha. Okay.
All right, can we talk about these? People seem to be working it out. And this is, this kind of a thing is what you should expect to see on our questions about this topic. So you do all of these derivatives. Hopefully you can kind of see a pattern. Now, in the previous problem, like the pattern was actually repeating itself. There's no repetition here, but I can see you always get e to the 2x along with some. These actually are powers of 2, right? This is 2, this is 2 squared, this is 2 cubed, and so on. So those are the derivatives. Then I'm going to plug in x equals 1, and I get these numbers. I just wrote the first 4 of them just because that was my job in this problem, write the first 4 non-zero terms. So, but if you wanted, you could easily write more than that. And then I'm going to put this together into my answer. So it'll say e to the 2x equals, and then each term here, remember, looks like the factorial part. Well, okay, the first term is just the first constant, which is e to the 2. This is a little strange looking, but that's the first constant, e to the 2. Now, this is kind of like the term 0. The real first term has 1 over 1 factorial, which is just 1, of course, and then this constant, 2e to the 2, times 2e to the 2, and then times x minus 1 to the power 1. That's the first degree term, as we call it. All right, that's the first one, and then we have 1 over 2 factorial times the next constant is 4e to the 2, and then x minus 1 to the 2. And then 1 over 3 factorial, 8e to the 2, x minus 1 to the 3, ... This, I hope this is what you got. Those are the first 4 non-zero terms. And if you wanted to write the next one, you could easily write the next one. It'd be 1 over 4 factorial, and then instead of 8, it'd be 16, and then e squared. Apparently, they're just all e squareds in there, and then x minus 1 to the 4. That would be the next term. What if I wanted to write that as a sum? It would say e to the 2x equals the sum. Somebody want to tell me? I know some people wrote something. What you got?
1 over n factorial to the n e squared times x minus 1. Sorry, x minus 1.
To the n. Yeah, I like that. Really, you just have to sort of look at one of these and tell what the pattern is. So first I see 1 over n factorial. Then I see this constant, which here is 8. That 8 is, the reason it's 8 is because that's 2 to the 3. So this constant here has this format, 2 to the n. And then I guess you just get e squared every time. So you put e squared every time. And then you have x minus 1 to the power n. Yeah, great. And if you want to write this sum here, when you're doing Taylor series, these sums always need to start at 0, n equals 0, because the very first term has a power of x to the power 0. So, all right, excellent. I think that's all I got. Thanks for finishing us off, Ainsley. The sole remaining Ainsley. Did you know there were 2 Ainsleys in the first week of class? But one of them changed into a different class. It was a shame to lose an Ainsley like that. 50% of our Ainsleys, but I'm glad you stayed with us, the other one. All right, that'll